Hello, everyone. Welcome. My name is Jean O'Connor. We'll get started here today. I'm a grant specialist in the Office of Research, and I'm here to briefly introduce our speaker. Our speaker today is Professor Yuhlong Lio, who has been a professor in the mathematics department at USD since 1987. He has produced over 100 research papers that cover computation algorithms, mathematics theories, and methodologies with applications to genetic data application, medical survival analysis, and industrial reliability. This presentation here today is titled Probability Modeling based on left truncated and right censored data for Marshall-Olgin bivariate distribution. Please join me in welcoming Professor Lio.
Thank you for a nice introduction before my talk. Now, everyone can see the title of my talk. Let us go ahead to move to the next page.
Oh, sometimes I just have to click it. Okay, now it's working. There you go.
Okay. This research actually motivated by the following two examples. Example one, diabetic retinopathy study conducted by the National Eye Institute. The purpose for this study to study the effect of laser treatment delaying the onset of blindness in patient. Now, experiment, the institute recruited 71 patients. For each patient, one eye was randomly selected for laser treatment. The other eyes was given no treatment. The data collected for each patient will be the minimal time of blindness from both eyes and the index to show the blindness from treated or untreated of both eyes. The second example, prostate cancer study reported by BR and Green in 1980, published in the Partition Cancer paper journal. In this paper, the author mentioned all the possible causes deaths for the patient can be classified into three categories: prostatic cancer or cerebrovascular or other causes. For this study, we may actually classify all the causes into two main causes. A, include prostatic cancer or other causes. B, include cerebrovascular and other causes. Now, the data collected again will be the minimal survival time for each patient due to cause A or cause B with index. Now, actually, what is the data in probability or mathematics? Because we don't have a real data on hand right now, we like to develop the formula for this case, so that after the data are collected, I can use the formula to do prediction and so on and so forth. So in mathematician, we call the data is random variable or measurable function. Now, I'm going to use this two Venn diagram to show the relationship between two causes. Now, cause A will happen if either observing factor 1 or factor 3. Cause B will happen if either observing factor 2 or factor 3. So factor 3 actually in the common location of this Venn diagram, right? So therefore, we can define the survival time for each patient due to cause A will be labeled by capital T1. The definition for capital T1 is the time needed to have either factor 1 or factor 3 to cause patient risk. Now, survival time for each patient due to cause B will be labeled by capital T2, defined to be time needed to have either factor 2 or factor 3 to cause the patient risk. So the patient risk due to either cause A or cause B. So therefore, the survival time for each patient will be defined to be the smallest value between capital T1 and the capital T2. So Rayleigh distribution have been a very flexible lifetime modeling distribution. So in this study, we assume patient's latent survival time due to 3 factors have Rayleigh distribution with different parameter sigma 1, sigma 2, sigma 3, respectively for factor 1, factor 2, or factor 3. So the density function have been established here, the density function, okay? The X input actually will be the survival time input. And the cumulative distribution function actually the integral of the density function from 0 to the upper limit, which is the input for cumulative distribution function. Now, you can calculate into this format. Survival function actually 1 minus cumulative distribution function. The survival function indicates the probability of the patient's survival time will be longer than this input time here. Now, these 3 functions will be used for our study. Now, in general setting, based on the capital T1, capital T2 definition related to factor 1, factor 2, factor 3 survival time. Now, this joint survival function can be defined to be the probability measurement for capital T1 greater than this small t1 input for capital T1. Now, small t2 input for capital T2 survival time longer than a small t2. But because the capital T1, capital T2 definition relate to x1, x2, x3, which are the surviving time for factor 1, factor 2, factor 3. So now this inequality can be furthermore to be represented in terms of x1, x2, x3. Okay. Now we understand since the capital T1 greater than small t1, we understand the smallest value for capital X1 and the capital X3 should be bigger than small t1. Similarly, capital T2 greater than small t2. So therefore, the minimum time between x2 and x3 will be bigger than t2, right? Using basic quality algebra, this inequality can be represented in this inequality. Okay, but represent in this way is easier for us to measure the probability because these 3 factors will be assumed to be independent factors. So anyway, if Rayleigh distribution had been applied for capital T1 and capital T2, then this survival function jointly can be developed to be a piecewisely defined function depending upon your first input greater than second input or less than second input or equal second input. By using this probability statement independence concept, you may go to factor into these 2 products. Okay, I'm going to skip the derivation for getting this piecewisely defined function. Okay, now, however, after I got the joint survival function, I would like to know the joint density function, right? The joint density function basically can be obtained through the joint survival function by using second order partial derivative with respect to T1 and the T2 separately. But however, the third piece of definition is very different because this is based on T1 equal to T2. You cannot take the derivative with respect to T2 here, right? Anyway, now to get the density function on the third piece, I like to use some other different way. But for these 2 pieces, I can simply to take a partial derivative to end this down. Okay, I'm going to skip this explanation. Let us move to the next one. After I have a joint density function and joint survival function for capital T1, capital T2, I would like to find the density function for capital T1, okay, and the survival function for capital T1, right? The derivation here a little bit complicated. I'm going to skip, okay? Basically, we establish a theory for this purpose, okay? Now, the marginal density function for capital T1 will be formed in this way. Marginal density function for T2 will be formed in this way. And the survival function has been defined before, right? Find his cumulative distribution function and then subtract by 1, okay? Then you will get the survival function presented here. Now, very obviously, you can see T1 actually relate to 2 factors, factor 1 and the factor 3, right? So therefore, the factor 1 parameter sigma 1 and the factor 3 parameter sigma 3 will be involved in the density function as well as in the survival function. Similarly for capital T2, right? Now, the survival time for each patient under the definition, which is the minimum survival time between capital T1 and capital T2. Of course, we can find the PDF for this guy will be in this format, okay, through a little bit more advanced probability concept, which will be skipped in this talk. Now, next, I'd like to represent the concept about the net truncated right sensor data. Now, the picture 1 actually sketch the net truncated right sensor data behavior under the study. Now, we assume each patient will be watching within a time interval. You may assume the net endpoint of the interval is appointment time for each patient. Okay. Now, the right endpoint of the interval can be considered to be follow-up time, right ending point. Now, this is a simple as a case. Okay. Now, we could have a more complicated, have a multiple appointment time schedule, but here we just have a one-time appointment schedule. Now, all the patients after have a further appointment time, they will under monitoring. Okay. Now we are going to use this time interval to monitor each patient. Now we have the following cases for our truncated right sensor data. Now the top one here presented this patient symptom starting point within the time interval, so we can record this time, right? And the risk also within this time interval, so we can see the true survival time for this patient. So this is called complete observation. Now here, the starting point happens inside the interval, but however, after the follow-up time schedule, the patient still survives. So I cannot complete observe the patient's survival time. So this case is called right sensor case. Okay. Now for the third case, the starting time actually before the first appointment, right? So I cannot observe this starting survival time, but the patient will survive through the time interval, and the next on the following up time, okay, still surviving for the patient. So in this case, we can see the time information actually truncated on the left ending and the sensor on the right ending. Okay, we know this patient have a survival time longer than this tau IR. Okay, we don't know his complete survival time at all. For the next line, you have a left truncated and no sensor, right? So this case is truncated and observe his risk time. Now, we never have this patient in my data set because the starting time and the risk time is before the appointment time for that patient. So this data never happened in our study. Now, after that, we like to understand what kind of data information will be collected. The data information for any recruited subject will be represented in this triple. Now, depending upon the delta, okay, value, which have been defined to be 1, 2, 3, 0. Now, 1 means what? This patient have a risk due to cause A. Now, when delta equal to 2 means the patient risk due to cause B. When indicate 3, okay, means patient have a risk due to both cause A and the cause B, right? That will be the common factor in between cause A and cause B. Now, for the right sensor patient, now this indicator will have an in output 0. Okay, so therefore we understand under when delta are equal to 1, 2, 3, you will have a true lifetime here, and also we can observe the cost for the risk, right? Okay, for the censored situation, I cannot observe the true survival time. Okay, the true risk time. The true risk time actually defined to be the minimum value of capital T1 and capital T2 for the ICE patient, right? Okay, then this T will be replaced by right sensor time, tau IR. Okay, tau IR. So I have an indicator I to indicate patient from 1 to 3, right? Now this also to indicate the observation time have a rough truncated, a left truncated or without left truncated, right? Now actually based on MOBR distribution for capital T1, capital T2, I can find the likelihood function for each case of the observation. Okay, given here. Now, how many cases I have? According to the data, I have 4 cases, right? Now, according to the new here, I have another 2 cases, right? So the combination, I will generate many cases for the likelihood function input. Now, I'm not going to address how to get this output because we established one theory to find the output for this likelihood function. This likelihood function is a little bit complicated. When you want to find the output, you also need to consider the possible impact from the other curves. Okay, so the very complicated situation here, but I would like to mention one important factor here. Sigma 1 sitting here indicate this likelihood function actually generated from the patient which have a risk due to cause A, Now here sigma 2 for cause B, right? So this likelihood function due to cause B, okay? Now this is sigma 3, right? Sigma 3 due to what? Both causes, okay? Now this is for right sensor situation. For right sensor situation, you just see the patient's survival time longer than the right ending point. So there's a probability to prevent the patient have a longer survival time greater than the right ending point. Okay. So another situation we are truncated. Now this case to indicate the truncated probability, we need to use this truncated probability to distribute the right truncated distribution. So therefore, we need to divide by k here. Okay, this is the 8 cases for likelihood function. What's the likelihood function? Likelihood function actually indicate the probability seeing this probability, seeing this data information. So I'm going to incorporate n patients likelihood function together to establish the whole patient's likelihood function. Okay, here I already include all the patients. All the n patients under the study can be classified into due to the cause A or due to cause B or due to both, right? Or maybe right sensor, right? So I have a correction here to indicate the correction of the patient have a risk due to A or due to B or due to B or due to right sensor. So by using the product principle, we assume all the n patients are independent. So you may go ahead to find the likelihood function for each patient should be the product of each individual patient's likelihood function. However, we can furthermore to classify all of the n patients per likelihood function product into these 4 main factors. Okay, 4 main factors. Now, in each factor of the product here, you can see non-truncated and the truncated, right? Non-truncated and the non-truncated, non-truncated and truncated, right? For the truncated, you have a k in the denominator. Okay, so sigma 1 here for the patient risk due to cause A, right? And so on and so forth. This is right sensor case, right? So after the simple algebra manipulation, combining like a factor together, you can simplify this likelihood function down to this level. But meanwhile, I would like to mention here, this is supposed to be the right sensor patient. I need to put the right sensor time here, right? But however, because their format actually the same as this one, the same as this one, the same as this one, I like to combine them together. So I just simply to represent the censored data for those type of patients, again, by using TI, such that I can put into the same term here. Of course, when we watch this formula and the data phenomena, we will be able to understand. We are going to add the survival time for those patients, which I can see the survival time and the right censored time into this summation, right? This is the truncated time, right? This guy is not so important. Let us move to the next one. Now, what is important about the likelihood function? I like to use the likelihood function to find the maximum likelihood estimator for the three unknown parameters, sigma 1, sigma 2, sigma 3. I'm sorry. The definition of the NLE actually is the maximizer for this function. Assuming sigma 1, sigma 2, sigma 3 are input. So we need to find the input value for sigma 1, sigma 2, sigma 3 to maximize the probability of getting this observation here, right? So that input will be the maximum likelihood estimate for each parameter. Now, however, we can take a partial derivative with respect to sigma 1, with respect to sigma 2, with respect to sigma 3, respectively, and set the partial derivative to 0. But however, with this kind of product, the partial derivative will be very complicated. So we have better to take logarithm to make to be summation. Then we can easily to apply the partial derivative. Then set those three partial order to first order derivative to be 0. You will find the solution for sigma 1, sigma 2, sigma 3 to be represented in this format. This is a new formula for us to use to do the estimate for sigma 1, sigma 2, sigma 3 in this study. No any other paper have produced this formula before. However, before the point estimate for sigma, we also need to find confidence interval for this unknown parameter, right? To find the confidence interval, we rely on sampling distribution for the estimator. But the true sampling distribution is difficult to obtain because the formula for estimator is quite complicated. The only random variable will be Ti, which represents the survival time for the patient. Okay, the right sensor time in here is not a random variable, so it's difficult for us to develop sampling distribution. But through a regular condition, okay, we can prove. Now all the three estimators joined together, okay, like a three-dimension vector. The multi-sampling distribution for these three dimension vector will have a central limit theory. Their distribution will approach to normal distribution with mean 0, 0, 0 for each of them. And the variance covariance matrix will be defined to be here. This central limit theory actually introduced in low-level statistics for one dimension, right? Like a sample mean as a population mean estimator. Then the sample mean sampling distribution have a normal distribution as the asymptotic distribution. Now, this central limit theory similar to that central limit theory. So therefore, I don't need to repeat. But here we have three dimensions. Now, this is what we call visual information, also three dimensions. Luckily, this visual information only have a diagonal element, not 0. The rest of position all in 0. So his inverse will be also that only diagonal have non-0. The rest of diagonal will be 0. This indicates all these three estimators are independent. So far so good. I'm going to use this to estimate the confidence interval as follows. By using a normal distribution, okay, normal distribution for his sampling distribution asymptotically, I can build the confidence interval. This confidence interval is actually the same as population means confidence interval when you use sample mean as an estimator. So this Z alpha over 2 actually is a critical point, can be obtained by using normal distribution, standard normal distribution, right? I'm going to skip the explanation here. This is a very important formula for our study in our research. And next, I'd like to introduce Bayesian estimator procedure briefly, but Bayesian estimation procedure quite complicated. You need to have a 3 components. One is what? A prior distribution for unknown parameter and the loss function to measure the loss of the estimate. Now, you have a square error loss function or absolute value error loss function. These 2 loss functions are commonly used in the application. Okay. Now, using the likelihood function I introduced for you earlier time, and the joint prior distribution. Actually, I have not introduced the joint prior distribution yet. Let's assume I already know. This together will be used for us to find joint posterior distribution. The joint posterior distribution actually proportional to this product. Now, I'm not going to go through a little bit more detail. Now, the prior distribution given here will relate to gamma density. Why? Because the parameter have positive value. Okay, so when the random variable have a positive value, gamma distribution will be a good modeling distribution. Now, we also use literal distribution for these 2 components so that I can deal with the possible dependency among these 3 parameters. So together we call the prior distribution or the gamma literal distribution. This is very complicated. We spend a lot of time to understand how to do sampling from here. But however, if we could find the posterior distribution for each parameter sigma 1, sigma 2, sigma 3, then we'll be able to find the Bayesian estimator for each parameter under the square error loss function. Then the estimator in Bayesian's approach will be posterior mean. Now, for the absolute value error loss, the Bayesian estimator will be the posterior median. So therefore, posterior distribution is the most important. But very often, including this study, the posterior distribution have no closed form. So in that case, we need to develop so-called MCMC sampling procedure. The MCMC means Markov chain and the Monte Carlo sampling procedure to get the sample from this product. I'm not going to introduce the detailed procedure because it's very complicated. Then we can use the producer sample information for sigma 1, sigma 2, sigma 3, respectively, to form the empirical distribution for sigma 1, sigma 2, sigma 3, respectively. Then we can use the mean of the empirical distribution for each estimator to find the Bayesian estimate. If I'm using the square error loss for the absolute loss, I need to find the median. Okay, so because the procedure very complicated, I'm going to stop here. Actually, in our research, we have Bayesian estimator result as well as a maximum likelihood estimator result. We established 5 important theories, okay, to deal with this estimation. We also create 2 computation algorithms to deal with Bayesian estimator. Now, in the rest of my presentation, I just want to do prediction by using frequency approach. The frequency approach means using maximum likelihood estimator approach. Now, typically, we like to predict the survival time for the patient under right sensor case. Okay, so the patient that for the study at the right ending monitor time interval, right? So we cannot see that patient's survival time because the patient that study still surviving, right? So therefore, we like to predict this patient's survival time. Now, according to MLOE procedure, I can prove the PDF in the survival function for that type of person, giving the survival time longer than the right ending point of the monitor time in the interval will be presented in this way for density function. For survival function will be presented in this way, right? So I can use these two functions to find the prediction of the median survival time, giving the patient surviving time longer than the right ending monitor time interval. Now, the formula has been developed to be this one for point estimate. Now, confidence interval based on survival function, I can find this interval. But this interval means this typical person have a sensor time at tau IR will survive in this interval with 50% chance because this is median survival time. But the point survival time will follow this formula, right? You can see we have right ending point sitting here in the formula, okay? So let us use all the formula developed in this study to do prediction for the first example, diabetes situation. Now, original sample actually is a complete random sample, not left truncated right sample. But however, to us mathematicians, we need to extend the random sample to be a little bit more general data set to include the left ending and the right ending monitor time, such that this data set actually contains my simple random sample. When the left ending point tau IL to be 0, then we don't have a left truncated, right? When I set my right sensor time to be infinite, then we don't have a sensor data. So of course, our data setting here, including random sample situation, so make our formula wider to be used, right? So however, I'd like to have some explanation about the data input from this example. Originally, the survival time is internal date. Okay, date will be the unit to measure the survival time. But however, when we are using a Rayleigh distribution, because we have an x square sitting in the exponential, okay, for e base, right? So I like to make my survival time measurement smaller. So I use 500 days as a unit. So all the survival time in this example will be divided by 500 to be the survival time in terms of 500 units for our study. We also set the truncated rate to be 20%, sensor rate to be 4%, such that I can using my simulation program to identify the patient should be under left truncated and the right sensor, okay, or both, right? No, I use my similar data from that 71 simple random survival time and plug into my formula, my estimate for sigma 1, sigma 2, sigma 3. After using 500 as a unit, MLOE estimator will be this guy. Okay, you got to time 500 to get true value for this one. And the confidence interval by using asymptotical distribution will be within this interval. For the partition time or the surviving, okay, for those patients under the sensor situation that happen at the 15 patient, 31 patient, 65 patient, the sensor time in terms of 500 unit day, okay, day as a unit will be presented here. Now, their likelihood point estimator survival median time will be this one, time 500. You got, median survival time after sensor time, okay? The confidence interval predicted here. Okay, again, you got to time 500 to get the true interval estimator. Okay, this is the end of my presentation. Of course, I did not have a chance to present all the research results because this research is very heavy, including Bayesian estimator. We essentially compare the estimation from MLE and the Bayesian situation. We find out in the Bayesian case, the estimation a little bit higher than MLE. The confidence interval a little bit have a small internal distance. Okay. Similarly, the median survival time a little bit higher than MLE, but the interval prediction have a smaller distance. Okay, smaller interval distance. Okay, this is about our research. Of course, we also do simulation. I'm not going to talk too much. Let us make a final conclusion. Now, you can see in my presentation, I can say statistics research is a data-driven mathematical research. The probability concept actually is used to deal with random issue. The objective is to create the novel formula to be used, right? So many events in real world are governed by chance, which can be indicated by the probability. So therefore, I think this approach is very useful in our life. Overall, this is a field mathematics. Okay, I probably can show you trick of mathematics, but I don't know I will be able to open this online page or not, because I tried in my office to have a little bit longer time. But anyway, the following is my personal information since I entered USD. Okay, let us go ahead. Well, I don't know how to do that. Let me see. You'll see in this tree of mathematics, actually statistics sitting at the top of the tree. Below statistics, you will see a lot of background. Okay, you need typically analyze the background. Okay, here we go. Oh, didn't show here.
Stop share and reshare.
Okay. Oh. Sorry, I cannot show you the tree of mathematics. Okay, generally speaking, the statistics actually sitting at the top of the tree. Below statistics, you have a lot of background, typically analysis, calculus, and then some other stuff. Okay. Now, this is the end of my talk.
I have a question for you.
Yes.
You've been at USD for a while, but your passion for this field hasn't wavered. What makes you excited to come to work every day?
Good question. Actually, I like math. Especially, I like to deal with math with a reality problem. Okay. I study at home. Okay. After dinner. So my life only teaching, meal, sleeping, study.
How do you feel about grading homework?
Grading homework. I have very good feel for grading homework because I can put all the paper for students together. I check the same problem, okay, to compare their technical, okay, use my background, use my answer. I can judge the partial credit. So I can finish grading easy, quickly. In that case.
Get that out of the way and then you keep studying.
Yeah.
Yeah.
Leo, can I ask you a technical question?
Sure.
So you use surveillance and my assumption is the same study can be done with different.
Yes, good question. Now I would like to mention, of course, here I speak a lot. I actually test by using simple random sample, as I mentioned, that was collected by the institute, right? I use the random sample to do modeling checking, okay? because Rayleigh distribution is a flexible modeling for survival time, and this distribution has not been studied for net truncated right sensor competitive risk model. So this is the open problem. So of course, in order to use this distribution, I need to do model checking, right? Now, there are very important model checking testing, which is called common seminal test, simply called KS test. KS test can be used to test to see your obtained random sample can be fit into Rayleigh distribution or not. Of course, you may use the same random sample to do some other model. Actually, you may go to test to see whether distribution is good modeling for this study or not. Actually, someone already have publication in that model. Okay, you may also check exponential distribution will be a good modeling for this data or not by using KS hypothesis testing. There are some other useful like lifetime modeling distribution, like a bird 10 and the bird 12, and so on and so forth. Here, I'm going to start here. Okay, so yes, we need to do modeling checking.
How do your results using the Rayleigh distribution as compared to the paper that used Weevil?
Actually, we didn't compare at this moment. Okay, and we really see the result from different papers. Some actually here, what I would like to mention, most people deal with this data as independent data, but probably our research is the only one to deal with dependent cost. Okay, because cost A and the cost B have a common factor, right? So therefore, cost A and the cost B actually not independent, like our two eyes. These two eyes controlled by our brain. They never work independent. Otherwise, we will have trouble, right? Okay. But however, most of research deal with this data case as independent data. So I cannot really compare.
Oh, I didn't follow all the math, but I was interested in the cancer one where you had people die of prostate cancer or cardiovascular or other. And I just thought A plus B plus C equals 1, right? I mean, everybody dies of something. I didn't know if that was a useful factor or not. You know, in other words, that's the whole world. The three Venn diagrams cover everything. Actually, here, as I mentioned, from the three different factors, for our study, I like to combine into two courses. One course is just have phosphate and A plus C or B plus C. Yeah. That is not mean plus. No, not mean plus. Oh. We just put all those cases together as a correction. All those patients having phosphate or other causes will be put into a one classification. Okay, we will measure their surviving time. Okay, and meanwhile we have cause B and the other cause right together. We measure their surviving time. Then we compare the surviving time. Okay. Yeah, that is doesn't mean it is.
Well, we're right up at the 1 o'clock mark. So we'll finish here things today, but thank you very much to our speaker and for everyone for attending.
Thank you.